Takis are the boldest and hottest chips on the planet, and the factory that makes them runs like a hyper-efficient machine. From precision rolling to a blast of extreme seasoning, every step is designed to deliver maximum crunch and spice. In this video, we're taking you inside the high-speed process of how Takis are really made. Few snacks on the market capture the attention of consumers quite like Takis. With their signature rolled shape, vibrant colors, and explosive spicy flavors, Takis have carved out a unique space in the world of extruded corn snacks. Originally created by Barcel, a Mexican subsidiary of the Bimbo Group, Takis have grown from a regional novelty to a global snacking sensation. But behind each intensely flavored bite is a fascinating and highly engineered manufacturing process that brings together agricultural science, mechanical precision, and food chemistry on a massive industrial scale. To understand how Takis are made in a factory, we must begin at the very first stage, the sourcing of raw materials. The cornerstone ingredient in Takis is corn, more specifically degermed corn flour, often referred to as mesa flour. This flour is derived from yellow or white field corn, grown primarily in the United States and Mexico. The corn used must meet specific quality parameters, particularly in terms of kernel size, moisture content, and starch composition. Contracted farmers typically grow this corn under strict agronomic practices to ensure high yield and consistent quality. Once harvested, the corn is transported to centralized milling facilities, where it undergoes a critical transformation. This transformation begins with the nixtamalization process, a traditional method that dates back to ancient Mesoamerican civilizations. In modern milling operations, dried corn kernels are steeped in a lime water solution, water mixed with food-grade calcium hydroxide at controlled temperatures for several hours. This chemical soaking loosens the hulls, softens the kernels, and alters the protein and carbohydrate structures, improving both flavor and digestibility. Once steeped, the corn is thoroughly washed to remove residual lime and loosen pericarp. What remains is nixtamalized corn, which is then ground through industrial stone mills or hammer mills into a fine, homogeneous masa dough. For Takis, however, the mesa is taken one step further. Instead of being used wet, as in tortilla production, it is dried and ground again into a shelf-stable mesa flour. This dried masa, now fine and moisture-free, serves as the primary input in the Takis production process. It's stored in massive silos within the factory, equipped with aeration systems to keep the flour dry and flowing freely. Pneumatic conveyors transfer the flour to precise metering hoppers above the mixing equipment. Here is where the transformation from flour to snack begins in earnest. The masa flour is dropped into high-capacity industrial mixers, where it is blended with water and a proprietary mixture of seasonings, emulsifiers, and sometimes oil. These mixers are equipped with temperature control systems and paddles designed to evenly distribute moisture throughout the blend. The goal is to create a pliable yet firm dough that is suitable for extrusion, a process that will ultimately define the iconic Takis shape. The mixed dough is conveyed directly to the extruder, a high-pressure, high-temperature piece of equipment that lies at the heart of many snack food manufacturing lines. For Takis, a twin-screw extruder is typically used. The dough is fed into the extruder barrel, where rotating screws push the material forward while simultaneously mixing, shearing, and heating it. Inside the barrel, steam pressure rises dramatically due to intense friction and controlled moisture. This heat gelatinizes the starches within the mesa, turning the dough into a malleable, semi-cooked matrix. At the end of the extruder barrel lies a die plate with specially engineered openings. These dies are shaped to produce flat ribbons of mesa with uniform width and thickness. As the dough exits the extruder, it experiences a sudden drop in pressure, causing it to puff slightly, though not excessively, as Takis are denser and more compact than puffy snacks like cheese curls. Automated blades Then cut the ribbons to a standardized length, usually between 4 and 6 inches. Now comes one of the most recognizable steps in the process, the rolling. Using a synchronized series of mechanical arms and belt-driven rollers, each flat strip is quickly rolled into a tight cylinder, mimicking the appearance of a small, rolled taco or taquito. This is done at high speed, often in under a second per piece, with careful calibration to prevent unrolling or uneven shapes. The rolling units must operate with precise timing and alignment, as even small inconsistencies could result in defective product or downstream clogging. Once formed, the raw Takis are transferred onto a mesh conveyor belt that carries them into the continuous fryer. Unlike air-puffed snacks, Takis achieve their final texture and flavor through frying in hot oil. The frying process occurs in large stainless steel fryers filled with high-stability vegetable oil, typically corn or sunflower oil. The oil is maintained at a consistent temperature, usually around 350 degrees Fahrenheit, and is constantly filtered and replenished to maintain quality and prevent flavor degradation. As the Takis pass through the fryer on a conveyor, they cook rapidly, the exterior crisping while moisture evaporates from the interior. This gives Takis their signature crunch, dense and satisfying, with just enough resistance to offer a unique mouthfeel. The fry time is carefully controlled, usually around 30 to 60 seconds, to ensure even cooking without burning or excessive oil absorption. Temperature sensors, oil flow meters, and automated timing systems monitor every batch, with defective products automatically rejected by vision systems downstream. As soon as they exit the fryer, the Takis must be cooled rapidly to halt cooking and prepare them for seasoning. The hot snacks are dropped onto a vibrating cooling conveyor, which uses forced, ambient, or chilled air to bring their temperature down quickly. This conveyor system not only cools, but also aligns and spreads the product evenly, preventing clumping before seasoning. And this is where the flavor magic happens. Takis are famous for their bold and intense seasoning blends, most notably the Fuego variety, which combines hot chili pepper and lime. The cooled snacks enter a large rotating tumbler or flavor drum, where they are coated with a fine mist of oil or flavor adhesive, such as maltodextrin or gum arabic. This light coating ensures the powdered seasoning sticks uniformly to the surface. Then, a precisely metered amount of dry seasoning blend is sprayed onto the rolling Takis within the drum. The tumbler rotates at a controlled speed, ensuring that every piece receives an even coating of the intensely red, flavor-packed powder. The powder itself is a carefully engineered blend of spices, acids, artificial flavors, and colorants, many of which are micro-encapsulated to preserve potency until consumption. This step is where flavor engineers shine, crafting bold profiles that hit the palate in waves. First, the citrusy tang of lime, then the slow-building burn of capsaicin from chili powder, followed by savory umami notes and salt. Once the Takis are evenly coated with their signature seasoning, the product advances to the post-seasoning inspection stage. Here, quality control takes center stage. As the finished snacks move down the conveyor belt, they pass through a combination of optical sorters, weight sensors, and human oversight stations. These systems are tasked with identifying any irregularities, broken pieces, improperly seasoned rolls, or foreign particles. High-speed cameras analyze each item against a programmed standard, with air jets used to automatically divert defective snacks from the production line. This meticulous approach ensures uniformity in every batch, both in appearance and taste. After clearing inspection, the freshly seasoned Takis enter the final phase of the production process: packaging. In large-scale manufacturing operations, packaging is not merely about enclosing the product in a bag. It's a tightly orchestrated, high-speed operation designed to maintain freshness, ensure food safety, and optimize shelf life. The cooled Takis are funneled into hoppers that portion them into individual servings. These hoppers are mounted above form-fill seal machines, or FFS machines, which are the heart of the packaging operation. Each FFS unit starts with a continuous roll of multi-layered packaging film. This film is typically made from a combination of materials such as polyethylene, aluminum, and polypropylene. These layers provide essential barrier properties, keeping out oxygen, light, and moisture, elements that would otherwise degrade the snack's flavor and texture. The film roll is unwound, shaped into a tube, and sealed along its vertical edge using heat sealing bars. Simultaneously, the bottom of the tube is sealed to form a pouch, into which a precise dose of Takis is dropped from the hopper above. As the filled pouch moves through the machine, a horizontal seal is applied at the top, closing the package and completing the bag. The result is a perfectly sealed, shelf-ready snack pouch. Some facilities also inject an inert gas, typically nitrogen, into each bag before sealing. This process, called nitrogen flushing, displaces oxygen and helps prevent oxidation of the oil and spices inside the snack. It's a key technique in preserving freshness for weeks or even months after production. But the packaging line doesn't stop there. Once sealed, the Takis bags are conveyed to the labeling and coding station. Here, high-speed inkjet printers apply critical data to each bag, including production date, batch code, and expiration date. These codes are essential for traceability, enabling both the manufacturer and regulatory bodies to track products through the supply chain and, if necessary, initiate a recall. In larger factories, barcode scanners validate each print in real time, flagging any unreadable or incomplete prints for immediate rework. Next, the finished snack bags are grouped into larger quantities for secondary packaging. Robotic arms equipped with suction grippers or mechanical claws pick up batches of bags and place them into cardboard cartons or shrink-wrapped bundles. These secondary units are ideal for distribution to retailers, vending machine suppliers, and food service channels. Automated case erectors, packers, and palletizers handle this stage with minimal human intervention, ensuring consistency and speed. Once boxed, the cartons are scanned one final time, then transported to the warehouse using automated guided vehicles or conveyor systems. The warehouse itself is climate controlled, maintaining ideal conditions for snack storage, typically around 70 degrees Fahrenheit and low humidity. Inventory management systems track every pallet, integrating with enterprise resource planning software to coordinate distribution across multiple regions and customer channels. At this stage, Takis are officially ready for distribution. Depending on the destination, pallets may be routed to regional distribution centers, export facilities, or directly to major retailers. In the US, this typically involves refrigerated trucks or dry vans with temperature and humidity monitoring systems to ensure the product remains in peak condition throughout transport. For international shipments, Takis are loaded into containers and shipped via freight lines, with each load accompanied by customs documentation, certificates of analysis, and food safety verification records. It's important to note that all these stages, milling, extrusion, frying, seasoning, packaging, and shipping, operate under strict regulatory compliance and food safety protocols. The Takis manufacturing facility is typically audited regularly by health authorities and third-party certification bodies to maintain good manufacturing practices and adherence to standards such as the Global Food Safety Initiative. HACCP, or hazard analysis, and critical control points is implemented throughout the line to identify and mitigate risks, from biological contamination to mechanical hazards like metal fragments. Metal detectors and X-ray machines are also integrated into the production line post-frying and pre-packaging. These systems serve as a critical control point, scanning every product to detect foreign objects that could compromise consumer safety. In the rare event a contaminant is found, the system immediately shuts down the line and activates traceability protocols, ensuring the source of the contamination is quickly identified and corrected. In addition to food safety, automation plays a crucial role in the consistency and scalability of Takis production. Modern factories are outfitted with CAD systems, supervisory control, and data acquisition, which allow operators to monitor and adjust every part of the process in real time. Temperature readings, fry times, dough consistency, seasoning distribution, packaging integrity, all of it is visible from centralized control rooms staffed by trained technicians. These systems also gather historical data, enabling predictive maintenance and process optimization over time. Moreover, the human element remains vital. Quality assurance personnel regularly conduct sensory evaluations to ensure the finished product matches the flavor, aroma, and texture profile that consumers expect. Samples are pulled at set intervals and subjected to detailed analysis, including moisture content testing, oil content analysis, pH measurements, and microbial testing. These assessments help maintain product consistency and detect any early signs of spoilage or variation. And let's not forget the environmental impact. Many modern snack food factories, including those producing Takis, are actively investing in sustainable practices. Waste heat from fryers is often reclaimed and used to preheat water or air elsewhere in the facility. Oil used in frying is filtered and recycled several times before final disposal. Packaging materials are increasingly being sourced from recyclable or biodegradable films, and energy-efficient motors and lighting systems reduce overall factory emissions. The success of Takis also hinges on innovation. Flavor development is a continuous process involving food scientists, sensory analysts, and marketing teams. New flavors are often trialed in small-scale batch lines within pilot plants, where formulation tweaks can be made rapidly without disrupting full-scale production. Once a new variety passes consumer testing, it's scaled up to the main line, where production parameters are adjusted to accommodate the unique characteristics of the new seasoning blend. In essence, every bag of Takis represents a fusion of ancient techniques and cutting-edge food science. From the Mesoamerican tradition of nixtamalized corn to the robotic arms and AI-controlled inspection systems of a 21st century factory, the journey from cornfield to snack aisle is a marvel of industrial engineering. The attention to detail, the layers of safety checks, the complex choreography of machines, and human oversight all come together to create that iconic crunch and fiery kick that snack lovers around the world have come to crave. Once the freshly sealed Takis packages leave the manufacturing floor, their journey is far from over. The next phase, post-factory logistics and storage, is just as critical to the integrity of the final product. From the moment those pallets are loaded onto the loading docks, every step must be meticulously orchestrated to maintain freshness, comply with regulatory requirements, and meet retailer timelines. Palletized shipments of Takis are typically staged in designated outbound logistics zones within the factory's warehouse. Here, inventory management systems, integrated with warehouse management software, guide automated forklifts or human operators in sequencing outgoing loads. Each pallet is tagged with RFID or scannable barcodes, providing traceable data like batch number, production date, customer destination, and handling instructions. This is especially vital in high-volume operations where hundreds of thousands of units move through daily. Distribution of Takis often begins with transfer to regional distribution centers, or RDCs. These massive hubs serve as strategic points between the manufacturing facility and the retail shelf. Transportation is conducted via trucks equipped with climate control systems to protect the product from temperature spikes or humidity, both of which could compromise the texture and flavor of the highly seasoned snack. Although Takis are non-perishable, they are still sensitive to environmental conditions due to the oil content and delicate nature of their fried, rolled structure. Upon arrival at RDCs, the pallets are unloaded and sorted according to their final destination. Some may be earmarked for export, requiring additional customs documentation and compliance with international food labeling standards. For domestic markets, the focus shifts to inventory allocation, wherein Takis are divided among retailers based on demand forecasts, sales trends, and marketing campaigns. Algorithms calculate optimal shipping routes and timelines to minimize storage time and maximize shelf life for consumers. In-store delivery typically occurs on a just-in-time basis. Retailers prefer to receive snack shipments shortly before they are needed for shelf restocking to reduce their own warehousing costs. Specialized delivery trucks make daily or weekly runs to supermarkets, convenience stores, gas stations, and even vending machine distributors. Each of these retail environments poses unique packaging and merchandising challenges, all of which were anticipated back at the design and branding stage of the Takis production cycle. One of the unsung heroes in the journey of Takis is the shelf life optimization strategy. Although the product is fried, which naturally reduces moisture content and microbial activity, the seasoning powders and oils are susceptible to degradation over time. To combat this, manufacturers employ a suite of preservation techniques. Nitrogen flushing, as mentioned earlier, displaces oxygen in the sealed package, but antioxidants like tocopherols or rosemary extract are often blended into the seasoning to prevent rancidity. Additionally, desiccant sachets are sometimes included in bulk packaging layers to absorb ambient moisture during long-haul shipping. Once Takis make it to the retail environment, product rotation and visual appeal become the next critical concerns. Merchandising teams work with stores to position Takis in eye-catching locations, often near checkout counters or in custom display racks. Packaging design plays a crucial role here. The vivid purple of the Fuego flavor, for instance, has become iconic. This is not accidental. It is the result of extensive consumer psychology research and competitive shelf analysis. The packaging is printed using high-intensity inks and UV-cured varnishes that resist fading under fluorescent retail lighting. Meanwhile, behind the scenes, the manufacturer continues to monitor product performance through various feedback loops. Point-of-sale data is constantly reviewed to identify hot-selling regions, seasonal trends, and underperforming SKUs. Social media sentiment analysis and direct consumer feedback also guide adjustments in flavor intensity, packaging size, and promotional strategies. All of this feeds back into the product lifecycle management software, which helps guide future production and flavor development decisions. Speaking of flavors, one of the most fascinating aspects of the Takis operation is the flavor innovation pipeline. Flavor development is not merely a matter of combining spices, it's a complex interplay of sensory science, market forecasting, and precision engineering. Within dedicated R&D facilities, flavor scientists and food technologists explore new seasoning blends that push boundaries while remaining accessible to a wide audience. Using a combination of gas chromatography, mass spectrometry, and trained sensory panels, they deconstruct flavor experiences into measurable data points. For example, developing a new flavor like Dragon Sweet Chili or Blue Heat begins with identifying flavor trends in regional and global markets. Are consumers leaning toward Asian-inspired profiles? Are younger audiences seeking spicier, more adventurous options? Once a flavor theme is chosen, food scientists begin formulating dry seasoning blends that meet those goals. These blends are then micro-encapsulated to maintain potency through the frying process, ensuring that the end product retains its flavor intensity after months on the shelf. Prototypes are created on small-scale extrusion and seasoning lines within pilot plants. Here, the entire Takis production process is simulated at a reduced scale. This allows for rapid testing of texture, color retention, seasoning adhesion, and oil interaction without interrupting full-scale operations. Multiple iterations may be required before the formula is finalized. Once approved, the new flavor is scaled up and introduced into the market through limited releases or promotional campaigns. Based on consumer reception, it may join the permanent lineup or serve as a limited time offering. But with every new flavor comes new challenges. Seasoning powders vary in density, oil absorption, and electrostatic properties, all of which affect how they adhere to the snack. The tumbler rotation speed, spray nozzle angle, and even drum temperature may need to be recalibrated to accommodate different blends. For spicy varieties, capsaicin levels must be carefully controlled not only for flavor balance, but also to comply with regional regulatory thresholds for spice labeling. Some jurisdictions require heat warnings if the Scoville rating exceeds a certain level. Furthermore, regulatory compliance is a continuous effort in every phase of production. Labels must accurately reflect ingredients, nutritional values, and allergens. In countries like the US, compliance with FDA labeling laws is mandatory. In the European Union, Takis must also adhere to FSA food additive regulations and translation requirements. This means each regional variant may have slightly different formulations or packaging to meet local standards. Another area of innovation is sustainability. Snack food factories around the world are under increasing pressure to reduce their environmental footprint. The Takis production chain is no exception. Some facilities have introduced biodegradable packaging options for select markets, while others have invested in solar panels and high-efficiency fryers to cut energy use. Spent cooking oil is now commonly collected and converted into biodiesel, and water used in nixtamalization is filtered and reused for non-contact applications like equipment cooling. Sustainability also intersects with supply chain ethics. Corn suppliers are vetted not only for quality and price, but also for compliance with labor and environmental standards. Supplier audits are conducted regularly, and digital traceability platforms are used to map the corn's journey from field to fryer. This level of visibility allows the manufacturer to ensure that every ingredient in a Takis snack aligns with their corporate responsibility goals. Takis, for all their fiery boldness and snackable appeal, are a masterclass in food engineering and global logistics. They represent what happens when cultural flavors are married with advanced manufacturing, when age-old ingredients are given new life through extrusion science, and when every detail, from the grind of the corn to the curve of the roll, is tuned for maximum consumer satisfaction. As the Takis brand continues to evolve, the role of emerging technology in snack production becomes increasingly pronounced. Digital twins, for instance, are now being introduced in advanced food manufacturing environments. These are real-time digital replicas of the physical production line, complete with sensors, predictive analytics, and machine learning algorithms. By modeling the entire extrusion and frying process digitally, operators can simulate how small changes in variables, such as dough moisture content, oil temperature, or seasoning particle size, will impact the final product before making physical adjustments. This minimizes downtime, reduces waste, and enhances consistency across batches. Artificial intelligence and machine vision systems are also revolutionizing quality control. High-resolution cameras paired with deep learning algorithms can now detect subtle flaws that human inspectors might miss, such as uneven seasoning, microfractures in the rolled snack, or variations in color that could indicate improper frying. These systems learn over time, refining their detection capabilities with each batch they analyze. This not only improves product quality, but also enhances traceability and accountability within the plant. One particularly forward-looking development is in the realm of alternative ingredient sourcing. As demand for gluten-free, vegan, and allergen-free snacks continues to rise, food scientists are exploring reformulations of Takis that use alternative flours, such as chickpea, lentil, or sorghum flour. These flours come with their own extrusion challenges, especially when it comes to texture and structural integrity. Specialized extruder screws and preconditioning treatments may be necessary to match the crispness and density of the original corn-based recipe. Flavor delivery is another frontier being actively developed. Microencapsulation technologies are growing more sophisticated, allowing for flavors to be released sequentially as the snack is chewed. This creates a dynamic sensory experience, perhaps a burst of lime followed by a wave of chili heat, then a subtle, lingering smokiness. These multi-layered flavor profiles are tested rigorously in consumer panels and sensory booths with metrics like aftertaste duration, palate burn intensity, and residual coating all logged and analyzed. All these innovations are feeding into a broader trend: personalization. The concept of mass-customized snacks, where consumers can choose their preferred heat level, flavor intensity, or seasoning combo, may soon become viable thanks to modular production lines and just-in-time mixing systems. Imagine entering a vending machine interface or online store where you could build your own Takis variant, which is then mixed and packed to order within minutes. The production of Starbucks products, particularly its packaged coffee offerings that end up in grocery stores, retail outlets, and international supply chains, begins long before a single bean is roasted. The entire process is built on one foundational element: green coffee sourcing. Starbucks, known for its commitment to quality and consistency, manages one of the most tightly controlled and globalized green coffee sourcing operations in the food and beverage industry. This first phase, the pre-roasting segment, is where the company sets the tone for every cup of coffee or bottled product it will eventually serve. And it's here we begin our highly detailed step-by-step journey. The green coffee sourcing process starts at origin in the tropical coffee-growing regions that straddle the equator, primarily Latin America, East Africa, and Southeast Asia. Starbucks primarily uses Arabica beans due to their more nuanced flavor profiles compared to the hardier but less complex Robusta variety. Within the Arabica family, beans are selected based on elevation, soil composition, rainfall, and harvest timing. Starbucks maintains long-standing relationships with coffee growers, cooperatives, and export mills in countries like Colombia, Ethiopia, Guatemala, Indonesia, Brazil, and Rwanda. But it's not as simple as ordering beans in bulk and having them shipped. Starbucks uses a proprietary set of sourcing standards known as Coffee and Farmer Equity Practices. These standards are not only a requirement for suppliers to be eligible, but also a multi-layered auditing framework. Cafe practices address 4 critical areas: product quality, social responsibility, environmental leadership, and economic transparency. Every farm or co-op that sells beans to Starbucks must pass rigorous inspections in these categories, many of which are carried out by third-party auditors trained in agricultural and labor practices. Once a farm or producer is approved under cafe practices, the beans are harvested, typically by hand. Hand-picking ensures that only ripe coffee cherries are selected, an essential factor in achieving flavor consistency in the final roast. These cherries are then processed at or near the farm using either the washed method. The washed method involves removing the pulp and fermenting the beans to eliminate the mucilage before drying, producing a cleaner, brighter flavor. The natural method dries the entire cherry and imparts a fruitier, heavier profile. The method used depends on the country, the farmer's infrastructure, and the target flavor profile desired by Starbucks blending teams. Once processed, the green beans are dried to a specific moisture content, usually between 10% and 12%, and stored in parchment until they are ready for export. Before leaving the origin country, the beans undergo a final hulling process to remove the parchment layer. At this stage, Starbucks' quality assurance teams at origin perform multiple assessments. These include physical evaluations and cupping, an industry-standard tasting method. Starbucks QA cuppers evaluate the green coffee on attributes like acidity, body, balance, sweetness, and aftertaste. Only those lots that meet Starbucks' sensory and structural requirements are approved for shipment. Approved beans are then packed into multi-layered jute bags with protective liners or into GrainPro plastic bags that guard against moisture and pests during transit. Each bag is tagged with a traceable barcode or lot number, which connects it to a digital database. This data includes not just the country and region of origin, but the exact farm or cooperative, harvest date, processing method, and quality score. This traceability is critical, not just for transparency and accountability, but also for quality replication year after year. Now begins the logistics phase. Starbucks contracts with specialized freight companies that understand the requirements of green coffee shipping. These beans are incredibly sensitive to temperature and humidity, even in raw form. A single exposure to high heat or excess moisture during transit can cause mold growth or flavor degradation. The beans are typically transported in temperature-stabilized shipping containers. If traveling by sea, the containers are outfitted with humidity control packs and dehumidifying systems. If air freight is used, the bags are carefully palletized, shrink-wrapped, and tagged with sensors that monitor environmental conditions throughout the journey. Upon arrival at one of Starbucks' roasting and manufacturing facilities, such as those located in York, Pennsylvania, Augusta, Georgia, Sandy Run, South Carolina, or Amsterdam, Netherlands, the green beans are unloaded, inspected, and entered into the factory's inventory management system. Before any production begins, each new shipment undergoes additional quality control. Samples from each bag or container are pulled and brought into the sensory lab. There, certified coffee graders perform cupping again, this time to ensure no quality loss occurred in transit. Moisture content, bean uniformity, and fragrance are retested. Beans that pass, these checks are tagged and routed to storage silos within the facility. These silos are food-grade, airtight steel vessels with internal climate regulation. Beans are stored based on variety, region, and intended blend. For example, Latin American beans destined for Starbucks blonde roast will be siloed separately from Ethiopian beans used in Starbucks Reserve offerings. Every silo is equipped with moisture sensors, thermometers, and pneumatic conveyor links, allowing operators to pull precise quantities for each roast batch according to master recipes. Before roasting can begin, beans are weighed into batches according to a specific ratio, depending on the blend being produced. Starbucks maintains an extensive library of proprietary blends, each with precise formulas. Some are single origin, where only one type of bean is used, while others, like Pike Place Roast or Espresso Roast, combine beans from multiple origins. Each blend is documented in the factory's recipe management software, which automatically calculates the needed amount of each component down to the gram and interfaces with weigh-scale systems to ensure accuracy. At this point, the beans are ready for roasting, but that process is highly intricate and deserves its own full analysis. Starbucks does not simply roast coffee by applying heat until the beans turn brown. The next step involves drum roasters, roast curves, heat profiling, airflow modulation, and real-time chemical transformation monitoring that will take the green coffee and convert it into the rich, aromatic, deeply flavored roasted beans that Starbucks is known for worldwide. With the green coffee beans now housed in precision-monitored silos and organized by blend formulation, the next phase of Starbucks' industrial production process transitions into what is often regarded as the heart of the entire operation: roasting. This stage is where the true transformation begins. The raw, pale green beans, earthy, grassy, and flavorless in their original state, are subjected to meticulously calibrated heat treatments that unlock their signature color, aroma, body, and complexity. Starbucks takes this phase extremely seriously, investing in proprietary roast profiles, customized equipment, and a multi-layered monitoring system to ensure that every batch matches the company's highly specific taste standards. The roasting process begins when a batch of green beans is called for from the storage silos. These silos are directly connected to the roasting equipment via stainless steel pneumatic transfer tubes. When an operator initiates a roast cycle, a preset quantity of beans, anywhere from 100 to 600 kilograms, depending on the size of the roaster, is discharged from the silo and transported through vacuum-sealed lines to the roaster's holding hopper. Here, the beans are pre-weighed on industrial platform scales connected to the plant's central production database, ensuring the exact quantity is delivered as dictated by the roast formula for that specific product, whether it's French roast, Pike Place, Sumatra, or espresso. Starbucks uses drum roasters for most of its large-scale production. These roasters consist of a rotating steel drum with an internal blade assembly that keeps the beans in constant motion. This ensures even exposure to heat as the drum is gradually raised to operating temperature, typically ranging between 190 degrees Celsius and 240 degrees Celsius, depending on the roast level. Lighter roasts, such as blonde roast, are roasted to lower final temperatures, while darker roasts, like French or Italian, require longer exposure and higher terminal heat. The roasting process follows a specific curve known as a roast profile. This is a data-driven graph that plots time against temperature, representing how heat is applied across the roast cycle. Starbucks profiles are proprietary and tightly controlled, with each product requiring a unique curve to deliver its intended flavor profile. These curves are not linear. They involve temperature ramps, plateaus, and even controlled dips. The initial drying phase lasts for several minutes, during which moisture is driven out of the bean. This is followed by the Maillard reaction phase, where sugars and amino acids begin to react, producing the rich brown coloration and the first wave of complex aromas. The most critical moment in roasting is known as first crack. This is when internal pressure in the bean causes it to physically crack open, producing an audible popping sound, much like popcorn. This marks a key transformation in bean chemistry. Starbucks roast operators listen for this moment, using audio sensors and thermal feedback to identify it precisely. Lighter roasts may be completed shortly after first crack, while medium and dark roasts continue through the development phase, where oils begin to emerge on the surface and flavor compounds deepen. Throughout this process, the roaster's control panel displays live data for bean temperature, exhaust temperature, airflow rate, and drum speed. The system is equipped with PID controllers and data logging software that feed into the factory's centralized SCADA system. Every roast is archived digitally, allowing Starbucks to recreate identical roast profiles across facilities on different continents, ensuring global consistency. Once the beans reach their designated roast level, they are immediately discharged from the drum into a cooling tray located below the roaster. This tray contains a rotating arm assembly that stirs the beans, while powerful fans blow ambient or chilled air upward from perforated grates below. Rapid cooling is essential to halt the roasting process and lock in the intended flavor and roast depth. If the beans are allowed to remain hot too long, they may bake, resulting in a flat, dull cup profile. The entire roasting to cooling process for a batch of coffee typically takes between 10 and 15 minutes, depending on the desired roast level and bean origin. Once cooled, the roasted beans are conveyed into degassing hoppers, stainless steel holding vessels, where the coffee rests for a short period, usually 12 to 24 hours. This rest period is necessary to allow CO2, a natural byproduct of roasting, to escape. If roasted beans are packaged too soon, the trapped gas can compromise packaging seals or even cause bags to inflate and rupture. However, some CO2 is desirable, especially for brewing freshness, so the timing of degassing must be carefully controlled. During this resting period, samples of each roast batch are collected and sent to the on-site sensory lab. Here, trained cupping teams evaluate the beans using controlled brewing and tasting protocols. They assess key attributes like aroma, acidity, balance, mouthfeel, finish, and overall quality compared to Starbucks' master profile for that roast. Cupping is performed blind and in duplicate to eliminate bias and ensure accuracy. If a batch falls outside of the acceptable range, it may be blended with other batches to correct the profile, used for internal consumption, or in rare cases, discarded. Once a roast batch passes quality inspection, it is routed towards the grinding and packaging area. Some products, like whole bean offerings, will skip the grinding stage entirely, while others destined for ground coffee bags or capsules will be milled using precision grinders. These machines are fitted with hardened steel burrs or rollers that crush the beans to an exact particle size distribution. Starbucks defines specific grind profiles depending on brewing method. For example, drip coffee grind is coarser than espresso grind, and French press is coarser still. Grinding is a highly sensitive operation. During the process, friction from the burrs generates heat, which can degrade volatile aromatics if not carefully controlled. To counter this, industrial grinders are equipped with chilled air systems and thermocouple sensors that regulate burr temperature and prevent overheating. In many facilities, grinding is conducted in a temperature-controlled room or during cooler hours of the day to preserve freshness. As soon as the coffee is ground, it moves to packaging, often through vacuum-sealed transfer tubes that prevent oxidation. The packaging stage is designed to preserve flavor and aroma while ensuring shelf stability. Starbucks uses multi-layer barrier films for its ground coffee products. These films include aluminum or metallized polyester layers that block oxygen and moisture. Many packages are fitted with one-way degassing valves that allow CO2 to escape without letting oxygen in, protecting the coffee's integrity while preventing package ballooning. Packaging machinery includes vertical form fill seal systems for smaller bags and horizontal form fill seal machines for pillow packs or multi-packs. Each package is filled to a specific weight, sealed, and coded with production data, including roast date, location, shift, and lot number. High-speed check weighers and vision systems verify fill accuracy, seal integrity, and barcode clarity. Any package that fails inspection is automatically diverted off the line for rework. After packaging, the coffee products are grouped into cases and transferred to automated case packers and palletizers. Pallets are wrapped and labeled, then stored in temperature-controlled warehouses before shipping. These final steps, inventory control, cold chain monitoring, and outbound logistics, are critical to ensure the roasted Starbucks product reaches distribution centers and retail shelves around the world in optimal condition. With the coffee beans now expertly roasted, cooled, rested, and either packaged whole or ground and sealed, Starbucks' industrial production extends into another critical manufacturing domain, the preparation of its ready-to-drink beverages. These include bottled frappuccinos, chilled espresso drinks, cold brews, and dairy-based coffee blends. These products are not created in the same facilities that handle roasting and bagging. Instead, Starbucks partners with specialized beverage manufacturing facilities. Many cooperated with industry leaders like PepsiCo through the North American Coffee Partnership to manage this high-volume cold fill production. This stage involves liquid formulation, blending, thermal processing, homogenization, and sterile packaging under rigid food safety standards. The process begins with the formulation of the beverage base. For a bottled frappuccino, for example, this includes several core ingredients: brewed coffee extract, filtered water, sugar or corn syrup, dairy or dairy alternatives, stabilizers, and natural or artificial flavorings like vanilla, caramel, or mocha. Each component must be handled separately with precision before it's brought into the blending system. Coffee extract is typically delivered in concentrated form, produced by either brewing Starbucks beans at scale or using advanced extraction methods like cold concentrate percolation or high-pressure brewing. This extract arrives in refrigerated, food-grade totes or tanker trucks, depending on batch size. Upon arrival, it is sampled, analyzed for strength, and approved by the on-site quality control team before entering the liquid ingredient holding tanks. Simultaneously, dairy components such as milk and cream are received through chilled pipelines or aseptic bag-in-box systems. Dairy intake systems in Starbucks RTD plants are equipped with plate heat exchangers to quickly chill and store milk at temperatures below 4 degrees Celsius to maintain freshness and prevent bacterial growth. If using shelf-stable milk or UHT-treated dairy, the plant will still hold the product under cold storage until use. For plant-based SKUs, oat milk, almond milk, or soy milk are stored and handled in similar systems, albeit through dedicated lines to avoid allergen cross-contamination. Sweeteners and stabilizers such as sugar, corn syrup solids, carrageenan, cellulose gum, and pectin are weighed and pre-mixed in separate tanks. Starbucks beverages are engineered not just for taste, but for texture, mouthfeel, and visual consistency, especially in cream-based products like bottled mochas and vanilla frappuccinos. The stabilizers help suspend coffee solids, prevent dairy separation, and ensure the beverage maintains a smooth, homogeneous appearance on shelf, even after weeks or months in cold chain storage. All of these components, coffee extract, dairy or alternative milk, sweeteners, water, and flavor compounds, are brought together in the blending system. This usually consists of large stainless steel jacketed mixing tanks ranging from 1,000 to 5,000 litres. Each tank is equipped with an internal agitator, a bottom-mounted high-shear mixer, and in some cases, inline emulsifiers or homogenizers to ensure all elements are fully integrated. Tanks are fitted with load cells and flow meters, enabling automated dosing of each ingredient according to pre-programmed batch recipes. The blending system is monitored via a central control unit, typically a PLC-connected touchscreen interface that displays real-time values for temperature, mixing speed, pH, and ingredient flow. Operators can monitor the tank's temperature curve, the shear level during mixing, and the dwell time of each phase. In a typical Starbucks RTD batch, the blending cycle lasts between 30 and 60 minutes. During this time, inline sensors monitor turbidity, Brix, and viscosity. Samples are taken periodically to verify pH, flavor intensity, and microbial load before the batch is cleared for downstream processing. Once the beverage blend is complete and validated, the next stage is thermal processing. Most Starbucks RTD beverages are pasteurized using high-temperature, short-time systems, which allow for rapid heat treatment without compromising taste or texture. In HTST, the product is pumped through a heat exchanger that raises the liquid temperature to 85 degrees Celsius to 95 degrees Celsius for 15 to 30 seconds, then rapidly cools it to filling temperature, usually between 4 degrees Celsius and 10 degrees Celsius for cold fill lines, or slightly higher for hot fill bottles. This process effectively destroys any pathogenic microbes while preserving the coffee's aroma and flavor. Some facilities use ultra-high temperature processing for shelf-stable lines, allowing the product to remain unrefrigerated until opened. In UHT, the beverage is flash heated to temperatures up to 140 degrees Celsius for just a few seconds, then cooled quickly before packaging. The decision between HTST and UHT depends on the specific product's shelf life goals, packaging type, and distribution model. Immediately following thermal processing, the beverage passes through an inline homogenizer. This device applies intense pressure, often in excess of 2000 psi, to the liquid through a narrow valve, breaking down fat globules and suspended solids into microparticles. This step is critical for emulsion stability, preventing the cream from separating from the coffee or the flavor oils from rising to the surface. Homogenization also improves mouthfeel, making the beverage taste creamier and smoother. From here, the liquid is conveyed to the filling system. Starbucks RTD products are filled into a variety of package types: PET bottles, glass bottles, aluminum cans, and aseptic cartons. Each format requires its own dedicated filling and sealing system. For bottled frappuccinos, a cold fill rotary filler is typically used. This high-speed machine feeds sterilized bottles onto a rotating platform, where they are filled by gravity or volumetric fillers to exact fill levels. Immediately afterward, caps are applied, using steam-assisted capping heads to ensure a vacuum-tight seal and tamper resistance. Cans and cartons are filled on their respective lines, cartons often using form-fill-seal machines that shape the container, fill it, and seal the top in one continuous motion. All packages pass through automated detection systems that verify fill levels using weight sensors, check cap placement with vision systems, and scan barcodes to confirm packaging accuracy. Reject mechanisms immediately remove any container that fails these criteria. The filled beverages are then passed through a secondary cooling tunnel or refrigerated spiral conveyor that ensures they reach their final holding temperature before entering the packaging area. Depending on the product, this may be as low as 2 degrees Celsius, especially for refrigerated drinks destined for grocery and convenience store cold vaults. Once cooled, the individual containers are collected into multi-packs, shrink-wrapped, and placed into branded cartons. These cartons are then palletized by robotic arms and wrapped with plastic film. Each pallet is labeled with a unique identifier, linking it to the specific batch number, production date, filler line, and formulation ID. All of this information is uploaded into the factory's ERP system, providing full traceability from bean to bottle. Before any shipment is cleared, final product samples are pulled from each pallet for comprehensive testing. These include microbial testing, shelf stability stress tests, and sensory evaluations by trained panels. Only after all tests are passed are pallets released into refrigerated distribution channels for delivery to retail partners, Starbucks cafes, or direct-to-consumer platforms. From formulation and blending to pasteurization, homogenization, and ultra-clean packaging, this RTD production phase represents one of the most technologically advanced parts of Starbucks' global supply chain. It's where liquid meets logistics, combining industrial food science with tight controls over quality, taste, and branding. Every chilled bottle or can represents thousands of interconnected variables managed with absolute precision to deliver a consistent, enjoyable Starbucks experience anywhere in the world. With Starbucks ready-to-drink beverages now filled, sealed, chilled, and palletized, the focus shifts to the final, but no less complex, elements of factory operations. Sustainability integration, byproduct management, batch auditing, and outbound logistics. While the product may appear finished at this stage, the systems behind its release are still active, ensuring every bottle or can shipped reflects the brand's uncompromising quality, environmental responsibility, and traceability. One major component of this final phase is waste stream management. Every Starbucks beverage production facility is designed to minimize waste and make use of byproducts wherever possible. Coffee grounds remaining from extract production are collected and either sent to composting facilities, transformed into animal feed, or, in more advanced plants, used as biomass fuel to generate energy. Spent dairy materials or cleaning water are filtered and treated through on-site wastewater management systems, often returning greywater to municipal treatment plants within strict pH and chemical parameters. Packaging waste, including edge trims from shrink-wrap film, carton misprints, and PET bottle scrap, is separated and sent to in-factory compactors and balers. These bales are transported to certified recyclers for reprocessing. Starbucks has implemented programs at several manufacturing locations that convert unrecyclable soft plastics into composite shipping pallets or building materials, helping close the loop on production materials. In parallel with waste management, quality auditing continues even after packaging. Randomly selected finished products are pulled from every batch and routed to a dedicated quality assurance lab within the facility. There, they undergo another round of microbiological testing, sensory analysis, packaging integrity checks, and accelerated aging simulations. These simulations might involve storing the product at elevated temperatures for several days or weeks to mimic what could happen during prolonged distribution delays. Any deviation in flavor, appearance, or microbial safety can trigger a hold on the entire batch while root causes are investigated. All data generated, from roast date to filler head temperature, from pallet wrap tension to microbial test results, is logged in the facility's centralized manufacturing execution system. This digital record ensures that any shipment can be traced back through every step of the factory process. If a product recall is ever initiated, these logs allow immediate identification of affected units by date, location, and even by hour of production. When cleared, the finished pallets are scheduled for outbound logistics. Route planning software, inventory analytics, and order data from Starbucks' retail and grocery distribution teams are combined to determine where each batch will go. Products destined for grocery stores enter the cold chain system, transported in refrigerated trucks with temperature logs monitored in real time. Others, such as shelf-stable offerings, are routed to ambient storage hubs or export terminals for international shipping. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold and they won't disperse evenly. Too hot and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of 2 primary components: a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase: baking. Meanwhile, The excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from overprocessing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts, equipped with vision systems, scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations. Bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal. The manufacturing process for Ruffles potato chips begins long before a potato even enters the production facility. It starts with agricultural planning and controlled sourcing. Ruffles, as a brand under Frito-Lay, utilizes proprietary potato varieties that are cultivated specifically for chip production. These aren't the same types of potatoes used for baking or mashing. Instead, Frito-Lay contracts with dozens of partner farms across the United States and other regions to grow chipping potatoes, varieties like Atlantic, Snowden, or proprietary Frito-Lay hybrids that are selected for their specific characteristics: high dry matter content, low sugar levels, uniform shape, and dense texture. Each crop is grown with tight controls on irrigation, fertilizer use, and harvesting schedules to ensure consistency and minimize storage degradation. Potatoes that are too moist, sugary, or irregular in shape would result in chips that are oily, dark, or fragile, none of which meet the Ruffles brand standard. At harvest, potatoes are collected using automated harvesters equipped with rubber conveyors that minimize bruising. They're loaded into transport trucks and sent to the factory, often within a few days of being pulled from the ground. When the potatoes arrive at the processing plant, they enter the facility through the raw receiving bay. These are enclosed intake areas where truckloads are weighed, logged, and tested before being accepted for processing. At this point, technicians from the quality assurance team extract random samples from the load to check for size uniformity, sugar content, starch levels, and moisture content. Any batch of potatoes that falls outside the tight specification window may be rejected or diverted to other non-chip product lines. Once cleared, the potatoes are offloaded from the trucks into a large receiving pit, essentially a hopper connected to a series of conveyor belts. From here, the potatoes are moved toward the initial cleaning phase. This begins with the destoning drum. As the potatoes enter this large rotating cylinder, jets of water and the rotating action cause heavier materials, like rocks or clumps of soil, to separate and fall through grated bottoms. Potatoes are lighter and are lifted to the next stage. From the destoning drum, the potatoes enter the pre-wash flume system. A flume is a water-filled channel that moves product gently using the flow of water instead of belts. This minimizes physical damage to the raw potatoes while removing dirt and loose debris. The flume water is treated and recirculated through industrial filters and chemical dosing systems to ensure both sanitation and water conservation. In many modern plants, the water used in these systems is part of a closed-loop recovery system designed to reduce environmental impact. The next stop is the rotary scrubber. This is a long, cylindrical machine fitted with internal brushes that rotate as the potatoes pass through. High-pressure nozzles spray water as the tub rotates, scrubbing away any remaining mud, sand, or biological debris. The inside of the scrubber is lined with abrasive surfaces that help clean the rough skin of the potato without cutting into the flesh. The goal here is to deliver a clean, undamaged potato with its skin still intact, ready for inspection. After scrubbing, the potatoes are lifted out of the washer by a cleated incline conveyor and passed through a visual and automated inspection system. In this phase, both human inspectors and camera-based vision systems work in parallel. The conveyor belt is engineered to spread out potatoes into a single layer, and each tuber moves past a combination of high-resolution cameras and infrared sensors. These systems are trained to detect green spots, bruises, cuts, or signs of rot. Any substandard potatoes are ejected via automated diverter arms or air jets, which remove the faulty items from the belt and send them to waste or compost streams. Human operators stationed along the line also remove visibly defective items that machines might miss, such as those with odd shapes that won't slice well on the crinkle-cut blades. Every removed potato is scanned and logged into the factory's waste tracking system, allowing operators to identify trends and address upstream sourcing problems if too many rejects appear from a single truckload. Now that the potatoes have passed visual inspection, they move on to the peeling station. For Ruffles, peeling is essential. While some gourmet-style chips retain their skins, Ruffles chips require a smooth, peeled surface to produce clean, consistent ridges during slicing. Peeling is achieved using a combination of steam and abrasion in what's known as a steam peeler. The steam peeler is a high-pressure vessel that receives a batch of potatoes, seals the chamber, and subjects the potatoes to pressurized steam, usually around 180-220 psi for 8 to 20 seconds. This superheated environment rapidly loosens the outer skin layer by partially gelatinizing the pectin between the skin and the underlying tissue. Once the steam cycle ends, a sudden pressure drop causes the skin to puff and detach slightly from the flesh. Immediately after this, the potatoes are discharged into an abrasive roller peeler. This is a rotating drum lined with rough surfaces, often embedded with carborundum grit, that gently scrubs the now loosened skins away. Water sprays are used to flush away the skins and clean the exposed potato surface. The amount of skin removed is carefully monitored. Too much abrasion would remove usable flesh and increase waste. Too little would leave patches of skin that affect the slicing process. The peeled potatoes are rinsed again in chilled water to stop any residual thermal activity and prevent enzymatic browning. A small dose of food-safe antioxidant, like sodium metabisulfite or citric acid, may be added to the rinse water to preserve the pale color of the peeled surface and prevent discoloration before slicing. At this stage, the potatoes are fully clean, peeled, and ready for their signature transformation, being cut into the iconic ridged slices that define a Ruffles chip. With the freshly peeled and rinsed potatoes now ready for transformation, the next phase in the Ruffles production process focuses on slicing, the moment where whole tubers are precisely cut into their distinctive ridged form. The ridges are far more than a visual or marketing detail. They play a critical role in the chip's strength, texture, and frying performance. This stage involves advanced slicing technology, careful temperature and starch control, and continuous monitoring to ensure each slice is the exact thickness, shape, and structural consistency required for optimal cooking and crispness. The peeled potatoes are transported to the slicing area via gentle, water-based flumes or soft conveyor belts to minimize impact and prevent bruising. Once they reach the slicing units, the potatoes are fed one by one into high-speed rotary slicers designed specifically for crinkle or corrugated cuts. These industrial slicing machines use a rotating impeller or feed wheel to press each potato firmly against a stationary, razor-sharp cutting head fitted with ridged blades. The blades are precisely machined to form a consistent wave pattern, typically with a wave amplitude of 1.5, 2.5 mm and a thickness of around 1.3, 1.5 mm. Unlike flat chip slicing, where a smooth blade is sufficient, Ruffles require a carefully engineered ridged blade made of hardened stainless steel. These blades are aligned at specific angles to produce even, undistorted waves along the chip's entire surface. The sharpness, speed of rotation, and pressure exerted must be perfectly balanced. Too much force or misalignment can result in chips with uneven ridges or broken tips, which would either fry unevenly or be rejected later during inspection. The sliced potatoes are ejected from the slicing drum at high velocity and collected in a shallow trough or on a belt that immediately begins the next critical step: starch removal and surface moisture control. Every potato contains natural starch, and when sliced, a large amount of that starch is released onto the cut surfaces. If not removed, this surface starch can interfere with the frying process, causing chips to stick together, fry unevenly, or develop burnt spots. It can also result in a greasy or gummy mouthfeel, which is unacceptable for Ruffles' clean, crisp texture. To remove excess starch, the slices pass through a multi-stage rinsing system. In the first phase, they enter a flume filled with cold, recirculated water, where they are gently agitated to dislodge free starch. The water in this flume is constantly filtered and monitored for starch content, with automated control systems adjusting flow rate and replacement intervals to maintain effectiveness. Following the first rinse, the slices often move through a series of cascading rinse curtains, sheets of filtered water that fall like waterfalls over the slices as they travel along a mesh or perforated conveyor belt. This helps remove residual starch without applying any mechanical force that could break the delicate ridges. After rinsing, the slices must be dried to a specific degree, not fully desiccated, but dry enough on the surface to allow the hot oil in the fryer to crisp the exterior without creating steam pockets or excessive foaming. This is achieved using a dewatering shaker and an air drying tunnel. The dewatering shaker is a vibrating belt or tray that shakes the slices gently to remove bulk water. The slices then pass under high-velocity air knives, rows of precisely aligned jets that blast room temperature or slightly warmed air across the chip surface. The air knives are tuned to create a shearing effect that strips away surface moisture while maintaining the shape and integrity of the ridged cuts. At this point, the slices are considered ready for frying, but only if they meet one final set of pre-cook inspection criteria. Before entering the fryer, the slices pass through an optical sorting system. This state-of-the-art inspection station uses a combination of high-resolution cameras, infrared sensors, and sometimes laser scanners to detect defects such as green spots, bruising, overly large slices, or broken pieces. Defective slices are rejected with microbursts of compressed air, which knock them off the main conveyor line and into waste or reprocessing bins. The acceptable slices, meanwhile, are evenly distributed across the width of the fryer in feed conveyor to ensure uniform exposure to hot oil. Frying is where the raw slices become what we recognize as potato chips. And for Ruffles, this step is both art and engineering. The chips are fried in continuous fryers, long stainless steel troughs filled with high-temperature cooking oil. The oil is typically a carefully formulated blend of vegetable oils, often including sunflower, corn, or canola oil, chosen for their high smoke points, neutral flavor, and oxidative stability. The oil is filtered, treated, and replaced on a tightly regulated schedule to maintain quality and avoid flavor degradation. As the slices enter the fryer, they are immediately submerged by a submersion conveyor that ensures they stay evenly beneath the oil's surface throughout the cooking process. The oil is maintained at a precise temperature, usually between 170 degrees Celsius and 190 degrees Celsius. This range is critical. Too cool, and the chips absorb oil and turn soggy. Too hot, and they brown too quickly or develop burnt notes. Each chip is cooked for approximately 2 to 3 minutes, depending on thickness, oil composition, and desired moisture content. Inside the fryer, the chips expand slightly and crisp as their internal water content rapidly evaporates. The ridged surface of Ruffles causes the chip to fry unevenly by design, creating micro variations in texture that result in a more substantial bite and greater structural integrity. The ridges also slow oil drainage, allowing a slightly longer dwell time that contributes to the chip's durability and resistance to breakage during dipping. The fryer is equipped with multiple sensors and flow meters that measure oil temperature, turnover rate, chip feed rate, and even in-oil moisture concentration. These data are analyzed in real time by the factory's central control system, allowing operators to make immediate adjustments. In many facilities, the frying process is linked to upstream slicing sensors. For example, if slightly thicker slices are detected coming from the cutter. The fryer conveyor speed is slowed accordingly to ensure proper cook time. As the chips emerge from the fryer, they pass through an oil draining phase. A vibrating conveyor with a perforated surface allows excess oil to drip off. This is immediately followed by an air cooling system that begins to lower the chip's temperature, halting further cooking and locking in texture. Cooling is essential not only for texture stability, but also to prepare the chips for seasoning, which happens shortly after. But before we get to seasoning, there's a critical interlude in the process: moisture analysis and inline quality control. At this stage, a small percentage of chips are diverted through a sampling chute to a nearby test station. Here, technicians use moisture analyzers, color meters, and even acoustic crispness testers to evaluate product characteristics. These tests ensure that the chips meet the factory's targets for final moisture content, color uniformity, and physical integrity. As the freshly fried and cooled Ruffles chips exit the fryer and pass through preliminary quality control, they enter one of the most dynamic and highly controlled stages in the factory: seasoning. This is the phase where the chips receive their final flavor identity, whether it's the original lightly salted variant, sour cream and onion, cheddar and sour cream, jalapeno ranch, or any of the other regional and seasonal flavor options Ruffles is known for. Applying these flavors evenly, consistently, and at high speed while preserving the chip's structural integrity and minimizing waste is a challenge that modern factories solve using specialized equipment and real-time process monitoring. The chips arrive at the seasoning station on a wide, inclined conveyor or vibratory tray that serves two main functions. It spreads the chips out into a single layer to prevent overlap, and it gently agglomerates chips to control their flow into the seasoning drum without damaging them. Due to the ridged shape and the thicker cut of Ruffles compared to standard potato chips, seasoning application must account for deeper surface area and variable orientation. Some chips will face ridge side up, some down, some angled. Seasoning application takes place inside a rotating tumbler drum, also called a flavor drum or seasoning cylinder. This stainless steel drum is set at a slight incline and constantly turns on its horizontal axis, gently lifting and tumbling the chips while they rotate through it. At the entrance to this drum, a continuous metered flow of seasoning powder is dispensed through an auger-based dosing system. The seasoning blend, pre-mixed according to a proprietary formula, includes a combination of salt, natural and artificial flavorings, cheese powders, dehydrated dairy, onion and garlic powders, spices, yeast extract, and anti-caking agents. The dosage rate of the seasoning is tightly controlled via real-time feedback systems. Optical sensors measure the chip volume entering the drum, and the dosing screw adjusts the delivery rate to maintain an ideal flavor to surface area ratio. Too much seasoning leads to clumping, over-salted chips, and waste. Too little results in bland or unevenly flavored chips that fail quality checks. For cheese-based seasonings, which are more moisture sensitive, the flow system may include a nitrogen-purged hopper or desiccant units to prevent clumping in humid environments. Inside the flavor drum, fine misting nozzles also spray a light coating of oil to help the seasoning adhere evenly to the chip surface. This atomized oil does not soak the chips, but rather creates a microfilm that holds the powder in place without compromising crunch. The rate of oil application, angle of spray, and temperature are all adjusted based on the type of seasoning used. For example, heavily coated varieties like cheddar and sour cream require more binder oil and a slightly longer tumbling duration to ensure every chip is fully and evenly coated. Throughout the seasoning process, line operators and quality assurance technicians take random samples every few minutes. These samples are assessed for seasoning coverage, color intensity, and surface powder levels. In more advanced factories, seasoning uniformity is checked with hyperspectral cameras that scan the chips as they exit the drum, detecting variations invisible to the human eye and triggering alerts or auto-calibration if inconsistencies are detected. Once the chips have been properly seasoned, they are transferred to the packaging phase. This is a highly automated and synchronized system that must meet several objectives simultaneously. Protect the chips from breakage, preserve freshness, prevent contamination, provide product information to the consumer, and maintain traceability for safety audits. Packaging begins with product accumulation. Conveyors from multiple seasoning drums may feed into a single accumulation hopper or weigher, depending on line configuration. This hopper temporarily holds chips before they're dispensed into individual bags via a multi-head combination weigher. A multi-head weigher is an advanced piece of equipment with multiple radial feed hoppers arranged in a circular pattern. Each hopper releases a small portion of chips, and a central computer instantly calculates which combination of hoppers adds up closest to the target weight, say 28.3 grams for a single serve bag. This combination is released simultaneously into a timing hopper, which drops the exact weight into a vertical form-fill-seal packaging machine. The VFFS machine forms bags from a continuous roll of printed plastic film, often made from multi-layer laminate materials with barriers against oxygen, light, and moisture. As the chips drop from the weigher into the forming tube, the film is pulled around the tube, sealed lengthwise, and sealed again at the top and bottom with heated jaws, creating a pillow-style bag. Before the top seal is made, a precise dose of nitrogen gas is injected into the bag, a process known as nitrogen flushing. This replaces the oxygen-rich air inside the package to reduce oxidation, extend shelf life, and protect the chips from crushing by slightly inflating the bag. Once sealed, each bag moves through a print station where batch codes, production time, plant ID, and expiration dates are applied using inkjet or thermal printers. Bags then pass through check weighers to confirm accuracy. Any bag outside the designated weight window is automatically rejected and diverted to a rework bin. Metal detectors or X-ray systems scan every bag to ensure no foreign objects have entered the product during processing. This is standard for all snack food production and a critical part of food safety compliance. From there, the sealed and verified bags are grouped into cartons or display trays by robotic case packers. These cartons are sealed with tape or glue and labeled with barcodes and tracking information. Finally, cartons are stacked onto pallets by robotic palletizers, often using suction cup grippers or clamp arms to gently stack without damaging contents. Pallets are wrapped in stretch film and staged in the finished goods warehouse, which is climate controlled to preserve chip texture and flavor. At every point along this packaging line, sensors, programmable logic controllers, and SCADA systems monitor performance metrics, line speed, reject rates, weigher accuracy, sealing temperature, film feed rate, and more. Maintenance logs and process trends are analyzed weekly to identify emerging issues, improve throughput, and reduce product loss. Beyond the physical movement of chips, there are strict sanitation and allergen management systems in place. Since some Ruffles flavors may contain milk, cheese, or other allergens, production lines must be deep cleaned between flavor runs. Clean in place protocols involve dismantling sections of the line using high-pressure washdowns, food-safe detergents, and microbial swab testing. Detailed records of every cleaning cycle are logged and audited regularly. In addition to cleaning, factories must manage cross-contamination risk during flavor changeovers. This includes running purge batches, segregating flavoring agents in separate storage silos, and using dedicated feed lines wherever possible. Every batch of Ruffles is linked back to a full traceability profile, covering raw material lot codes, equipment used, line operator IDs, and environmental conditions during processing. As the freshly packaged Ruffles chips leave the main production floor, the final phase of manufacturing comes into focus. A sophisticated web of logistics, sustainability efforts, continuous process optimization, and digital innovation. While the chips themselves are complete, the factory does not pause. Instead, a parallel system of data analysis, quality assurance, and supply chain orchestration continues operating in the background, ensuring the product not only meets current demand, but evolves to meet future expectations. These behind-the-scenes processes are integral to the long-term efficiency, environmental responsibility, and market success of Ruffles. At the heart of these operations is a factory-wide data infrastructure that tracks every input and output, from raw potatoes to finished pallets. Each batch of Ruffles produced is logged into an integrated manufacturing execution system. This software records the origin of each ingredient, the time and conditions of each processing step, the performance of every machine along the line, and even environmental metrics like room humidity and oil turnover frequency. The MES integrates with enterprise resource planning systems, providing real-time visibility into inventory levels, sales forecasts, and raw material consumption. This data is not merely archived, it's analyzed continuously using advanced analytics platforms and AI-based algorithms. These systems look for patterns in machine downtime, chip reject rates, oil consumption per batch, or seasonal fluctuations in potato solids. If a fryer begins to show a subtle increase in oil absorption, or if seasoning coverage becomes slightly more variable, the system flags it. Maintenance crews and process engineers receive alerts and can intervene before the issue affects product quality or efficiency. Predictive maintenance models also help avoid equipment failure by identifying when motors, pumps, or slicers are approaching wear thresholds. One of the key areas of focus in modern Ruffles factories is oil management. Frying oil is both a major cost and a major variable in product consistency and sustainability. The oil in the continuous fryer is constantly recirculated through filtration units that remove chip fines and particulates. Inline sensors monitor the free fatty acid content, color, and total polar materials in the oil, 3 indicators of oil degradation. When these metrics exceed defined limits, the system initiates partial or full oil replacement protocols. Some facilities have implemented smart fryer systems that dynamically adjust oil flow and heat profiles based on chip load and moisture level, significantly reducing oil turnover without compromising flavor or texture. Environmental sustainability is another priority embedded into Ruffles manufacturing. Frito-Lay, the parent brand, has committed to reducing water, energy, and greenhouse gas emissions across its snack food plants. One way this is achieved is through water reclamation. The flume water used to transport, wash, and rinse potatoes is filtered, UV treated, and reused multiple times before final disposal. Similarly, the steam peelers are equipped with condensate recovery systems that recycle steam condensate back into the boiler system, conserving energy and reducing water use. Electricity usage is optimized through variable frequency drives on conveyors and pumps, while LED lighting, motion sensors, and insulated cooling tunnels help minimize unnecessary energy waste. Some Ruffles production plants are now partially powered by renewable sources, including solar panels and biogas captured from on-site food waste digesters. Waste heat from fryers is recovered using heat exchangers and used to preheat incoming wash water, further boosting energy efficiency. Waste management is another crucial part of the factory's operations. Trimmings from biscuit cuts, chips rejected for size or overcooking, and seasoning overage are all collected, logged, and sent to animal feed processors or converted into biofuel when food safety protocols allow. Even the excess oil removed during de-oiling phases is collected, filtered, and sold to biodiesel manufacturers. Packaging materials are optimized for minimal plastic use, and packaging engineers continuously evaluate new laminates that offer better barrier performance with reduced environmental impact. Historically, gum base was made from natural tree resins like chicle, a latex-like substance harvested from the sapodilla tree, which grows in Central America. However, nearly all modern bubblegum factories now rely on synthetic gum bases. These are specially formulated blends of food-grade elastomers, resins, waxes, plasticizers, and softening agents. The use of synthetics provides far greater control over consistency, shelf life, and bubble blowing capability, which is critical for mass production and distribution. The raw materials used in synthetic gum base are delivered to the factory in large sacks or drums, and each ingredient is sampled and tested before entering the production line. Elastomers such as polyisobutylene and polyvinyl acetate provide the stretchy, elastic properties needed for bubble blowing. Resins act as binders that hold the gum together. Waxes like paraffin and microcrystalline waxes are added to soften the mixture and give the gum its pliable, non-brittle chew. Plasticizers such as glycerol, esters improve texture, while fillers like calcium carbonate or talc give the gum body and density. Each of these materials must be prepared for mixing. Solid components are broken down using industrial grinders and micronizers to achieve a uniform particle size, which ensures even distribution throughout the base. Waxes and resins are often pre-melted in jacketed stainless steel tanks equipped with indirect heating systems to prevent scorching. The raw elastomers are delivered in dense, rubbery blocks that are cut down using industrial dicing equipment before being added to the mix. Accuracy in measuring each component is vital. The slightest deviation in the amount of resin or wax can drastically alter the final chewiness and bubble forming capability of the gum. Now it's time for the blending of the gum base, which happens in large Sigma blade mixers, named for their two interlocking Z-shaped blades that rotate in opposite directions to fold and knead heavy materials. These mixers are specifically designed to handle high viscosity compounds like gum base. The various pre-measured ingredients are added to the mixer in a specific sequence. First, the elastomers are introduced and given time to soften and break down under shear force. As they begin to form a uniform mass, resins are added to bind the structure. Waxes and plasticizers follow, blending smoothly into the mixture to help reduce internal friction and improve processability. This mixing process is not quick. Depending on the size of the batch and the recipe, the blending cycle can last anywhere from 45 minutes to several hours. The mixer itself is equipped with internal thermocouples to continuously monitor the temperature of the mass, which is maintained between 60 degrees Celsius and 90 degrees Celsius. Too low and the materials won't melt and blend. Too high and thermal degradation could occur, affecting the safety and performance of the gum. Operators observe the process through viewing ports and rely on torque readings and viscosity data from the mixer's internal sensors to determine the exact moment the gum base is fully homogenized. Once the gum base has reached the correct consistency, it is discharged from the mixer. This is a challenging step because the base at this point is extremely thick, sticky, and hot. To facilitate removal, the bottom of the mixer opens hydraulically and the heavy base is dropped onto a large stainless steel cooling table or fed directly into a sheeting system. The cooling table is actively temperature controlled using circulating chilled water to begin lowering the temperature of the gum base as quickly and evenly as possible. Large Teflon-coated rollers may be used to flatten the mass slightly, increasing surface area and speeding up the cooling process. The goal at this point is not to bring the base down to room temperature entirely, but to reduce its temperature to a workable range, usually between 40 degrees Celsius and 50 degrees Celsius, so it can move to the next stage without sticking to equipment or losing its plasticity. The partially cooled gum base is then cut into manageable blocks using high lubricity heated cutting blades. These blocks are weighed, labeled with batch numbers, and either sent directly to the next phase of production or stored in temperature-controlled holding rooms for later use. Even in this early stage of production, quality control is already an active part of the process. Samples of gum base are collected from each batch and taken to the plant's in-house laboratory, where technicians test them for elasticity, tensile strength, softness, and melt behavior. Specialized equipment such as rheometers, durometers, and texture analyzers are used to measure mechanical properties under simulated chewing conditions. This ensures that the gum base will respond correctly when blended with sweeteners, flavors, and colors in the next stages of processing. It's also worth noting that not all gum base formulations are the same. For bubblegum specifically, the formulation includes higher levels of elastomers and plasticizers than in chewing gum intended for long-lasting flavor or dental benefits. Bubblegum is designed to be more pliable and capable of trapping air, so it can form large bubbles without breaking too easily. This performance requirement influences everything from ingredient selection to mixer settings and even downstream cooling methods. Therefore, each variation of gum base may require its own unique process settings and equipment parameters. In the next stage, the base will be transferred into another high-capacity mixer, this time designed to handle not only dense material, but also sensitive flavor components and volatile sweeteners. The balance of heat, pressure, timing, and sequencing here is critical. Too much heat can break down sugar molecules and destroy flavor integrity. Too little, and the gum won't mix properly. The entire system must operate like a symphony of mechanical precision and food engineering science to ensure that every piece of bubblegum delivers the iconic chew and flavor burst that consumers expect. With the gum base now fully prepared, cooled, and tested, it's time for one of the most critical stages in bubblegum manufacturing: the integration of sweeteners, softeners, and flavorings. This is where the bland, rubbery core transforms into something enjoyable and familiar. The sweet, fruity, chewy product capable of inflating into perfect pink bubbles. At this point, the gum base is still a nondescript mass, pliable, tacky, but utterly flavorless and unappealing. The magic is about to happen in an industrial mixing process that must blend these next components evenly while preserving the precise texture and chew required for successful bubblegum performance. Before anything is added to the gum base, it must be brought back to a specific working temperature. Though the blocks were cooled after being discharged from the original base mixer, they must now be re-softened for further blending. This is accomplished using a series of jacketed holding vessels or warming conveyors that apply gentle, indirect heat, usually via hot water or steam circulating through double-walled stainless steel pipes. The temperature is carefully raised to a range of 40 degrees Celsius to 60 degrees Celsius, just enough to make the gum base pliable again without overheating or causing degradation of any of the soon-to-be added ingredients. The resoftened gum base is then introduced into a second type of mixer, often a horizontal batch mixer or a planetary mixer specifically engineered to process high-viscosity food materials. These mixers are outfitted with double sigma blades or paddle arms capable of kneading the gum base with immense force. Once the gum base begins to rotate and fold, the sweeteners are added gradually. These include powdered sugar, also known as icing sugar, glucose syrup, and sometimes corn syrup solids. Each of these sweeteners serves multiple purposes. Powdered sugar provides bulk, texture, and long-lasting sweetness. Glucose syrup contributes a softer mouthfeel and prevents crystallization. Corn syrup solids help maintain chewiness and shelf stability. In some formulations, especially those designed for sugar-free bubblegum, bulk sweeteners such as sorbitol, xylitol, or mannitol are used in place of sugar. These polyols require different handling due to their moisture absorption characteristics and sensitivity to heat. In any case, each type of sweetener must be fed into the mixer in stages, allowing the gum base to fully absorb and integrate the new material before more is added. This prevents clumping and ensures that the resulting mixture remains smooth and pliable. Industrial-scale screw feeders or vacuum conveyors may be used to introduce these ingredients directly into the sealed mixing chamber to maintain cleanliness and prevent contamination. Following sweetener addition, softeners such as glycerin and vegetable oils are introduced. These materials are essential to prevent the gum from becoming brittle over time and to give it the desirable, soft, elastic texture that bubblegum is known for. The quantity and timing of softener addition are precisely calculated. Too little and the gum will harden quickly after production. Too much and it will become greasy and sticky, especially under warm storage conditions. Glycerin, in particular, helps trap moisture within the matrix of the gum and acts as a plasticizer, allowing the final product to retain its chew even after prolonged shelf life. Once the bulk of sweeteners and softeners are integrated, it's time for one of the most delicate and carefully timed steps in the entire production line: the addition of flavorings and colors. Flavor compounds used in bubblegum are typically a blend of fruit, esters, vanillin, and long-lasting artificial flavors engineered specifically for gum applications. These flavors must be oil-soluble and thermally stable, as any degradation can result in bitterness, loss of intensity, or altered taste profiles. The most iconic bubblegum flavor is a blend of banana, cherry, cinnamon, clove, and wintergreen, artfully balanced to create that familiar pink taste that people associate with classic bubblegum. These flavoring compounds are often concentrated liquids or emulsified pastes, and they're introduced in the final stages of mixing to preserve their volatile aroma compounds. If added too early, the heat and shear of the mixer could evaporate or chemically alter them. The flavors are poured in slowly while the mixer runs at a reduced speed, allowing gentle incorporation. Some manufacturers use pre-encapsulated flavor beads that dissolve slowly during chewing, extending flavor release over time. Coloring agents are added simultaneously or immediately after. These are usually food-grade dyes, such as Red 3 or Red 40, depending on regional regulations, and are added in liquid form or as pre-dispersed powders. These colorants are not just about visual appeal, they help consumers identify and associate flavor with appearance. For classic bubblegum, the universal hue is a bright bubblegum pink. The dye must be evenly distributed throughout the batch, and to do this effectively, the mixer must achieve total homogeneity without overworking the gum or exposing it to heat that could cause the color to fade or change. During this final blending stage, the entire gum mass is constantly monitored. Operators inspect the mixture for uniformity, gloss, elasticity, and color consistency. Samples may be extracted from the mixer at regular intervals and manually kneaded or stretched to ensure no streaking or spotting. Texture and pliability are tested by compressing and stretching a small piece by hand or using mechanical texture analyzers. If any inconsistency is found, whether it's too stiff, too soft, uneven in color, or lacking in flavor, the batch may be reprocessed or scrapped entirely, depending on the deviation severity. Once the gum reaches the desired final formulation, it's discharged from the mixer onto a temperature-controlled rolling table. At this stage, the gum has taken on its familiar look and feel: soft, elastic, vibrantly colored, and bursting with aroma. However, it's still a massive block of uncut material, far from the small, uniform pieces sold in stores. To prepare it for shaping and portioning, the gum is flattened using motorized rollers that compress it into thick sheets. These rollers are heated just slightly, enough to keep the gum pliable, but not so hot that it becomes sticky or begins to sag. The sheeted gum is then conveyed into a sizing line, where it passes through multiple sets of progressively narrower rollers to reduce the sheet thickness to the exact target for the final product. Whether the gum will be cut into strips, rolled into tape, molded into spheres, or formed into pillow-style pieces depends on the final product format. The sheet thickness must be precise. Too thick, and the gum will be too large to chew comfortably. Too thin, and it will tear or lack substance. Precision slitter blades then slice the gum into long ribbons, which are cooled again on conveyor belts using ambient air or chilled tunnels. These ribbons are stacked and allowed to rest briefly in temperature, dent, and humidity-controlled zones. This rest period, sometimes called the conditioning phase, allows moisture and elasticity to equilibrate across the entire piece of gum. It helps stabilize the internal structure and prepare the gum for cutting, shaping, and packaging without causing cracking or deformation. At this point, bubblegum is fully formed in its raw shape, but still unwrapped and unpackaged. The product is ready for the next phase, which involves high-speed forming machines, wrapping systems, and final packaging lines designed to handle thousands of pieces per minute. These systems require their own precise engineering and synchronization to maintain the integrity and appeal of the final product. Now that the bubblegum has been properly flavored, colored, sheeted, and rested, it enters one of the most mechanically intricate and visually satisfying stages of production: shaping and cutting. At this point, the gum exists in long, flat ribbons of pliable, glossy material, carefully rolled and stacked in conditioned zones to ensure uniformity and stability. These ribbons are conveyed in single file onto a forming line that uses high-speed, synchronized mechanisms to turn raw sheets into the iconic forms consumers recognize, whether small pillow-style pieces, sticks, chunks, tape rolls, gumballs, or extruded logs. Let's first explore the most common format, the pillow-shaped bubblegum piece. This format is familiar from vending machines, Halloween candy mixes, and individual wrappers. To achieve this, the bubblegum ribbon is fed into a forming wheel, where it is gently guided through a series of progressive molds or cavity rollers. These rollers are designed with alternating male and female cavities that press into the gum from both sides, creating the shape of a small rectangular block with softened edges. As the ribbon passes through these molds, the gum is compressed and cut simultaneously by a synchronized die cutter positioned just after the final molding wheel. Cutting must be done with extreme precision, as even a millimeter of deviation could affect packaging alignment and product weight. To account for thermal expansion and gum elasticity, the cutting blades are adjustable in both depth and cycle timing. High-speed optical sensors detect the flow rate of the gum ribbon, feeding data into a digital controller that dynamically calibrates the cutter's speed in real time. The gum, now formed into uniform bite-sized pieces, is ejected onto a short conveyor, ready for wrapping. In the case of bubblegum stick formats, like the flat rectangular pieces found in classic packs, the shaping process is slightly different. Instead of molding with rollers, the gum sheets are trimmed on all four edges to create clean, sharp lines. They are then passed through a rotary cutter equipped with hardened steel blades, slicing the sheet into strips of exact dimensions. These strips are stacked and cut again to create individual sticks. The machines responsible for this operation resemble guillotines, but with servo-controlled precision that allows for continuous, non-stop operation at high speeds. The final sticks are conveyed into wrapping units without any manual handling, preserving hygiene and maintaining throughput. Bubblegum tape, a novelty format often rolled into small plastic canisters, requires its own unique process. The sheeted gum is passed through a winding station where it is gently rolled into a flat coil, not unlike a roll of tape. Tension is carefully controlled here, too much pressure, and the coil will deform or stick to itself. Too little, and it will unravel inside the container. Once coiled, the tape is automatically dropped into a custom-formed plastic shell, usually hinged with a pop-top lid. A blade inside the lid allows consumers to tear off a desired length. These plastic cases are injection molded on-site or sourced in bulk and fed into the filling line by vibratory bowl feeders. For gumballs or spherical bubblegum formats, the production method is even more specialized. Instead of being formed from ribbons, these are made using extrusion and spheronization techniques. Warm gum is extruded through a nozzle into a thick rope, which is then cut into small segments by a rotating knife. These segments are dropped into rotating pans, lined with friction-inducing surfaces that tumble the gum continuously, rounding the pieces into spheres through centrifugal motion. Once the balls reach a near-perfect shape, they are cooled and coated in a separate process, which we'll explore shortly. Regardless of the final shape, all bubblegum formats at this stage are unwrapped and uncoated, meaning they are vulnerable to sticking, moisture absorption, and contamination. Therefore, the next critical phase is the wrapping and packaging process, which combines high-speed automation, material engineering, and branding considerations. Starting with pillow pieces and sticks, the gum is immediately conveyed into primary wrapping machines. These are high-speed horizontal or vertical flow wrappers, capable of wrapping hundreds of pieces per minute. A continuous roll of printed film, typically made of polypropylene or foil-backed paper, is unwound and fed through the machine. As the gum pieces travel along a conveyor, the film wraps around each piece and is sealed using heated crimpers that create a back fin seal and two end seals. For some classic styles, twist wrapping machines are used instead, which pinch both ends of a small rectangular wrapper and twist them tightly around the gum. These machines are equipped with sensors that detect gum position and length, ensuring perfect alignment between the product and its printed branding. If even a single wrapper is misaligned or improperly sealed, that piece is ejected from the line via pneumatic diverters. Wrapped pieces are then collected, counted, and transferred in bulk to secondary packaging machines. Secondary packaging is where individual units are grouped for retail sale. For stick gum, this may involve stacking 5 or 10 wrapped sticks into a flat paperboard sleeve, then shrink wrapping the pack. For pillow gum, machines automatically count the desired number of pieces and drop them into a pre-formed bag, which is then sealed using heat or ultrasonic welders. Packaging films are chosen for durability, oxygen resistance, and visual appeal, and often include tear notches or resealable zippers for convenience. In the case of bubblegum tape, filled plastic canisters are labeled and moved through a shrink sleeve applicator, which places a heat shrink label around the container. This sleeve serves both branding and tamper-evident functions, and is tightened using a controlled burst of steam or radiant heat. Finally, canisters are packed into display boxes or larger cartons using robotic pick-and-place arms. Now we return to gumballs, which undergo a unique finishing step: sugar coating. Unlike other formats, gumballs are coated in a hard, shiny shell that not only protects the gum inside, but also adds flavor, color, and gloss. This process is performed in large stainless steel coating pans that slowly tumble the gumballs while successive layers of syrup and powdered sugar are applied. The syrup typically contains water, glucose, and food coloring, which adheres to the surface of each gumball. Then a layer of sugar or sugar alcohol-based powder is sprinkled over the syrup, sticking to it and gradually building up a thick shell. Each coating layer must be dried before the next is added. Warm air is blown gently into the pans while the gumballs tumble, ensuring even drying without cracking or warping the shell. After multiple layers are built up, sometimes more than a dozen, the gumballs are ready for polishing. This final step involves applying a thin layer of food-grade wax or shellac to the gumballs to create the glossy, reflective finish that's so iconic. The polished gumballs are then cooled, inspected, and fed into bulk bagging or capsule dispensing systems depending on their final use. Throughout the forming, wrapping, and packaging process, real-time quality control continues at every junction. Vision inspection systems verify wrapper alignment, seal integrity, and color consistency. High-speed check weighers ensure that every package contains the correct number of pieces and meets the stated weight. Metal detectors and X-ray systems scan for any foreign particles or processing defects. If a flaw is detected, the package is automatically ejected and flagged for review. And behind all of this automation is a digital infrastructure tracking every batch, from base production through to final packaging. Every piece of bubblegum can be traced back to the exact shift, mixer, raw ingredient lot, and even the machine operator responsible for that run. This traceability system is essential for food safety, quality assurance, and regulatory compliance. Once bubblegum has been fully processed, formed, wrapped, and inspected, it enters the final phase within the factory: storage, quality verification, and preparation for shipment. Although the gum is now finished, it still requires careful handling to ensure that its quality and integrity remain intact all the way through to its final retail destination. The post-production environment is just as controlled as the manufacturing zones. Finished goods are transferred into climate-regulated storage areas, where temperature and humidity are strictly maintained to preserve the texture, flavor, and packaging condition of the gum. Each product pallet is labeled with QR codes or barcodes that carry essential traceability information: product type, batch number, production date, and expiration code. These codes integrate with warehouse management systems that organize inventory by shelf life and destination. The warehouse operates on a strict first in, first out (FIFO) system to make sure the oldest products are shipped first, reducing waste and ensuring consistent freshness in the marketplace. Before any product is released for shipping, quality control teams perform final checks. Samples from each lot are pulled and tested for packaging seal integrity, gum softness, visual consistency, and flavor. Any package that fails inspection is flagged, and the rest of its batch is reviewed. All quality records are logged digitally, tying back to the original gum base formulation and mixing parameters. This robust traceability ensures that, in the rare event of a defect or recall, every package's full production history is instantly accessible. Once cleared, the products are palletized and prepared for outbound delivery. Some are shipped to retail distributors, others to vending machine companies, export terminals, or wholesalers. Trucks used for transport are checked for cleanliness and proper loading temperatures to ensure the gum isn't exposed to heat or humidity during transit. Stretch-wrapped pallets are loaded according to weight and stability guidelines, scanned out of the factory system, and then dispatched. Even after leaving the facility, each batch of bubblegum remains traceable, monitored, and accountable. This level of post-production oversight is essential to maintaining brand reliability and consumer trust. It ensures that the bubblegum purchased in a corner store, supermarket, or theme park tastes exactly as intended: sweet, chewy, stretchy, and perfectly made. From polymer blending and base formulation to flavor integration, shaping, wrapping, and final logistics, the entire bubblegum production process is a seamless combination of food science, mechanical precision, and quality management. It's a surprisingly complex journey for a product designed to be fun and carefree, proof that even the most playful confections are supported by a foundation of serious, sophisticated industrial engineering. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated. separated into single file and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking. And an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the Almond Joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coated, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers, and the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final